Welcome! In this lecture we are going to look at how the control of HVAC components works in general terms. This is about the control of the operation. First, we need to get a general idea how control works. In the basis, it is very simple. A control loop describes what you want to have, what we actually have now, and which actions should be taken to get closer. For instance, I want a temperature of 25 degrees in my house. Set point temperature is 25 degrees. I measure the actual temperature, it is 29 degrees Celsius. I compare both here and see they are not equal, so I undertake the action belonging to this situation, and which is cooler should be switched on. As long as the measured temperature is not equal to the set point, the cooler remains on. From the moment the measured value equals the set point or is lower, the cooler will be switched off. You see here immediately a small problem arising, and that is the problem of oscillations. If the temperature is just above 25, the cooler will be switched on, and if it is just below, it will be switched off. So the cooler will continuously switch on and off, trying to achieve exactly this value of 25 degrees, producing very short on-off cycles that are damaging to mechanical equipment. That is why the control set point will never be a value, but a range of acceptable values. For instance, not 25 degrees Celsius, but everything between 24.5 and 25.5. For each parameter we want to control, the control loop consists of 4 different elements. What we measure is called the sensor system. What we want to have is the set value. The controller is the part that makes the analysis of the measured value, compare it to the set point, and decide which action should be taken. Finally, the actuator consists of the elements of the system that carry out the needed actions, for instance, switching on or off the cooler. To make a control system, we need to be aware of our control objectives. Which parameters do we want to control? For instance, the temperature. In that case, we need to choose the right temperature sensor and to set the right set point value range. We then need to be aware of the possible actuators. In our example, which elements of my HVAC system needs to be activated or deactivated to influence the parameter we want to control. In the case of temperature, it may be switching on or off a cooler or a heater, opening a window or putting solar blinds down. This type of control loop is called a feedback control loop. The sensor provides feedback to the controller, helping him to make the decision. Before looking at sensors, controllers and actuators, we need to determine which parameters we want to control in the HVAC system, and this in relation to the parameters we want to control at room level. The primary aim of buildings' energy systems is to ensure continuously a comfortable and healthy indoor climate. As we have seen throughout this course, it is first about temperature, having the right indoor air temperature. When an air handling unit is used, we'll need to control the temperature of the conditioned air being supplied to the room. And we also need to ensure the right surface temperatures, resulting in the right mean radiant temperatures. The surface temperatures are partly determined by the degree of insulation. We have no operational control on that, but also partly by the temperature of the emitters, determined by the temperature of the water flowing in the emitters, the hydronic system. So in the end, we need to control air and water temperatures. The second objective of HVAC systems is to provide enough clean air, by which we need to control the air volume flow rates. Volume flow rates and pressure are tightly interrelated, so let's add pressure here as well. As it comes to pollutant control, we will not handle it here. We saw in other part of the course that there are methods like source control by using the right materials, filters, UV cleaning, etc. We now just consider that enough volume flow rate is helping with pollutant control, and we don't address it as such. Third, in many climates, we also need to control indoor air relative humidity. And finally, remember the importance of air velocity and turbulence for the thermal comfort in rooms. This must be controlled as well. Both these parameters depend on airflow rates and pressures at the outlet of air valves. It also depends on their position. That will be the subject of another lecture. We don't handle it here. So in the end, the control parameters of any HVAC system are reduced to only 4. Temperature, pressure, and volume flow rate, and relative humidity. Let's start with the control of volume flow rates. That's the basic and also the most easy, as the actuator acts directly on the parameter to be controlled, the flow rate. Valves and dampers are the way volume flow rates are controlled in ducts once the needed pump and fan power is present. A damper is just another name for an air valve. These valves are named two-way valves and are represented in P&IDs by the symbol above. In a water duct, the two-way valve looks like this. Above the valve is open, below it is closed, and of course in controllable valves all positions in between are possible. You see on these pictures how it looks like. The two on the left are manual and the ones on the right are motorized, so it can be controlled automatically. The motorized ones are the ones that are used for the automated control of HVAC systems. The one below right is a valve for an air duct. It is more simple than for hydronic ducts. It is just a circular slice that rotates to open or close the duct. In this picture, it is open. The control loop looks like that. The flow is measured by the sensor, and if it is not in the right range, action is undertaken, meaning that the valve's position, which is the actuator, is changed. It is a feedback loop, so the sensor is placed after the actuator and sent back to the actuator, and send signal back, and the actuator acts according to the value measured after the valve. In a P&ID, this is indicated like that. Look above right. The actual value of the flow, VV, is measured by a flow sensor sending its signal to the controller, which compares it to the set value Vs after what action is undertaken on the valve. That is the meaning of the red dotted lines. It sends a signal. So, somewhere after the valve there is a sensor placed on the duct. Pressure and volume flow rate controls are completely linked with each other. Changes in pressure result in changes in flow. Changes in volume flow rates result in changes in pressure, as you may remember from another lecture. So even the two-way valves and dampers we've just described have an influence on the pressure. However, sometimes we really need a pump or a fan to overcome high static pressures resulting from the natural decrease of flow velocity, referred to as dynamic pressure, due to the flow losing kinetic energy because of friction along the pipe's wall. Pumps and fans add this missing kinetic energy to the flow by adding pressure on it. They push the fluid up, let's say. The picture above shows an air duct with a fan. The second one, a water duct with a pump. We'll explain the working on the second one. It is exactly the same with a fan. As pressure and flow are so linked together, the sensor used may be either volume flow rate sensors, as described in previous slide, or pressure sensors, like a pitot sensor, described in another lecture. But how can we influence the pressure? In other words, what are the actuators? Well, there are three ways of doing it. The first two ones cause a lot of energy waste and arise from the times that pumps and fans could only rotate full speed, so the incoming flow could not be controlled and was always full flow. The first way is to squeeze the flow after the pump using a two-way valve, which is named throttling. When the opening in the duct is reduced, the velocity of the flow decreases before the valve, so the static pressure increases, meaning that the resistance to the flow increases and less volume is pumped, while the pump still runs at full velocity, wasting a lot of energy. The second way is to bypass a part of the flow after the pump, also using a two-way valve, and to re-inject it into the duct just before the pump. This way the velocity of the flow increases before the valve, so the static pressure decreases, the resistance to the flow decreases, and more volume is pumped. The pump still runs at full velocity, while only a part of the pumping power is used for the needed flow, wasting this way a lot of energy. Much better, and done in most modern pumps and valves, is to control the rotational speed of the pump. A pump or fan is a rotating thing compressing the fluid. If the speed of rotation increases, the pump makes more cycles and more fluid is compressed, leading to a higher volume flow rate, and conversely. This way, the power of the pump is continuously adapted to the needed flow and pressure. This can save up to 50% of the pump energy in comparison with the first two options. You see here an example of such a pump with above pressure sensors and below the electromotor driving the pump and controlling the rotational velocity. Let's look now at temperature control. In this case, the sensor is a temperature sensor, of course. But what about the actuator? Well, basically, there are three ways to control temperature, and that is either by bringing or removing heat from the fluid with a heater or cooler, which we'll see later, or by mixing the flow with another one having another temperature. You studied this possibility in a course about mixing of humid air, but you can do the same in an hydronic system. Finally, as that is what you see in this picture, temperature can also be controlled by allowing more or less flow rate to a heater, cooler, or heat exchanger. Q is mCp delta T. This could be, for instance, a thermostatic radiator valve before a radiator, like you see on the picture. We can also control temperature by using a three-way valve. In fact, it also controls the flow. There are many parts of a HVAC system where heat is removed or gained, like a boiler, a cooler, and all kinds of heat exchangers. The rectangle with plus minus symbolizes such a heat exchanger on the right, a cooler or a heater. In general, one wants to make sure that the temperature after this device, T3, is well controlled and remains between strict values. This is of course for the largest part done by the cooler, heater or heat exchanger, but depending on its working and the secondary flow it depends on, it may be that T3 is not always achieved. That is when the three-way valve is used. Let's take the example of a heating mode. In that case, T3 is higher than T1. If T3 is lower than expected, then a part of the flow in branch 3 is diverted and mixed with branch 1 at T1, increasing this way T1 to T2. As T2 is now higher, T3 will be higher as well. You see here how the flows are divided. Such a control can also be used to control flows. The temperature sensor may then be replaced by a flow sensor. You see here how such a three-way valve works, and on the picture below you see the electromotor actuating the valve. Most evidently, temperature control can also be done by heating or cooling a fluid. In that case, a temperature sensor measures the temperature and the actuator takes care that more or less heat is delivered or taken away. When the heater is a gas boiler, switching the boiler on means opening the gas supply valve and starting the ignition and switching the circulation pump on. In the case of a chiller or a heat pump, that will be switching the compressor on and the pump or the fan. In general, these processes are already automated in the boiler, heat pump or chiller. Next to switching on and off, it is also possible to control the speed of the compressor in heat pumps and chillers and the volume flow rate of gas in boiler. This way a smoother control is obtained and more energy is saved. If the heater or cooler is a simple heat exchanger, like in a solar boiler or ground heat exchanger or district heating, the flow rates can also be controlled the same way. You may remember from another lecture that relative humidity can be determined by measuring simultaneously the dry bulb temperature and the wet bulb temperature. A wet bulb thermometer is just a thermometer wrapped in a humid cloth. So, this time, we have two sensors. The controller has a lot of decisions to take and to send to the actuators. First, it must calculate the relative humidity using the two temperatures. If it is too low, humidification can be activated, for instance by switching on the pump of the adiabatic humidifier. If the humidity is too high, then cooling and reheating must be activated. For these two parts, temperature control, as described in previous slides, is needed. So, there are control loops asking other control loops to come into action. Each air handling unit has its own controls. The room control communicates with them through an interface. You now probably understand why automated building energy management systems are needed, especially in large buildings. There are sometimes hundreds of controls developed either by the producers of components like heat pumps, boilers and valves, either by the HVAC control engineers. It all must fit together, and that is quite a thorough job. In a building energy management system, the sensor data are collected before being processed and analyzed. There are a lot of developments in this area of building automation, as artificial intelligence and machine learning just start to be used to help in these tasks. In this lecture, we studied the working of a control loop and saw the importance of using a range for the set value. We saw that in a control loop there are sensors, controllers and actuators. In general, only 4 different types of parameters need to be controlled: pressure, flow rate, temperature and relative humidity. For each of these parameters, we described which actuators can be used to control them and which actions the actuators can undertake. In the end, with only 2-way valves, 3-way valves, rotational speed and heater and coolers, we can come a far end. Thank you for your attention. Goodbye.